Okay. Hey, everybody. I'm James. I'm a faculty member at Georgia Tech. I was also at Argo AI. Well, anyway, I'll have a word about that in a second. I'm going to be presenting this. I'm just going to give a brief intro before Kyle and then Nihar and then Tarasha present over the next hour or so. And first, let me thank the organizers. This is an awesome workshop. This is our 5th time presenting these competitions at this workshop, and there's been an astounding amount of progress made on these benchmarks on everybody else's. So thank you, except that you made us speak right after Sonia, and that's rough. Anyway, so I'm just going to talk for a few minutes about an overview of Argoverse and then hand it over to Kyle to talk about that scene flow, and then we'll go through the rest of the competitions. So Argoverse 2 is really 4 different data sets, each with a collection of different scenarios that all have some common traits. For example, they all have HD maps. That means lane level geometry, things like lane markings, crosswalks down to the centimeter level. They were all gathered by autonomous vehicles that Argo operated in 6 US cities, pretty diverse places with different weather, different architecture, different pedestrian behavior, things like that. The first data set, which was the basis of some of the competition, so Nihar will talk more about this, was the sensor data set. And I think this is what you traditionally think of when you think of an autonomous vehicle data set, and that it's, it's the LiDAR data, the stereo data, the camera data with 3D annotations of where things are in the world. Argoverse 2 is a little different from other really influential data sets like the Waymo data set and New Scenes, in that it tends to have more annotations at range, all the way out to 200 meters, basically the LiDAR range. And it has a more fine-grained taxonomy than those data sets. But otherwise, it's broadly similar to those types of data sets in scale and the types of tasks it supports. And again, every scenario has an HD map underneath it as well. The LiDAR data set is not as widely used, which is why I'm happy to promote it here, is that it's 20 times as many scenarios, and each scenario is twice as long. So it's a tremendous amount of LiDAR data collected in the real world. There's not 3D object annotations. In fact, there's not even imagery in this data set. It's already terabytes with just the LiDAR returns. But if you want to do self-supervised learning with LiDAR, this is a great data set to try it with. It does, again, have HD map annotations with every scenario. Moving on, the motion forecasting data set has been probably our most widely used set of data sets in these challenges and otherwise, and we will, again, present some competitions that use these data sets. These are non-perceptual data sets, so what you're seeing there are tracked objects from the real world. The tracking is imperfect, so the object position and velocity might be imperfect as well. But we track 10 different object classes, and the task is to predict the future, basically, to say, well, this object that we're interested in moved this way over the past 5 seconds. What does it do in the next 6 seconds? Nihar will go into more details about this. And then another data set, the final data set, which is not widely used, but again, if you want to set state of the art on something, this is probably a good one to try it on, is the map change data set. And I think it's again, fairly unique. So the task here is to be able to say that my AV with HD maps has come upon a real world scenario where the sensors are showing things that don't match with my maps. And this will happen in the real world, right? Robotaxis tend to use HD maps, but the real world changes. And so this data set contains actual scenarios where the Argo fleet encountered this. So what you're seeing on the left there are visualizations of recently repaved roads. The city added a bicycle lane or moved the lanes. And so at some point, the AV has to, for the first time, encounter these and realize that, hey, my map is stale, fall back to some limp mode, start real-time mapping or whatever. Or I guess other people would argue, well, you shouldn't be using HD maps at all. I'm not convinced by that yet. But anyway, yeah, these are real scenarios like that. If you do want to get started with Argoverse, we have a user guide to help you. Just Google Argoverse user guide. You can find it. And yeah, the Argoverse team is pretty big now. Again, Argo doesn't exist anymore. It's been shut down for about 2 years. So most people here were affiliated with Argo in some capacity. But now this is the community's data set. It belongs to us. They gave us the keys to the kingdom, which was super nice to us. So there's no more corporate oversight of this data set. It's just us, the people in this room. So if you have something that you want to do with a data set, you're like, oh, I think these data sets are using the wrong metrics, so they're not benchmarking a task that I care about, then come talk to us, because we can stand it up and maybe that'll be the next challenge for next year, something like that. So I have 4 goals for this set of presentations before I hand it over. 1, we should learn about what's new, the state of the art for all of these competitions that we ran. 2, we should celebrate the teams that made really cool contributions and give them the credit for what they've done. 3, again, I'd like you to be interested in Argoverse and go try it out. And 4, if you do try it out, I'd like you to go further and actually contribute, have your photo up here next year because you are running a challenge that we thought was interesting. Okay, with that, I'm going to hand it over to Kyle, and he's going to talk about the unsupervised scene flow competition.
Thank you. Yeah, so on the list of new challenges, this one's pretty new. We did it for the first time last year, and we changed the metric for this year. So we'll talk about that as we get into it. So first, why do we care about cars but not trees? Cars move, right? When you're driving in the real world, you typically care a lot about the movers because they aren't just static obstacles that you need to avoid. So what is scene flow? It's the task of predicting between 2 point clouds motion vectors on a per point basis. So you can see here a car, right? The original point cloud was the dark green one. The orange one is the T+1 time step. And the red vectors are the flow vectors that you're basically trying to predict on a per point basis between them. So the way we get labels is we have amodal bounding boxes describing the full volume of the points over time. And the motion of these boxes, right? Motion from T to T+1 describes a rigid transform, and we can use that to get per point motion vectors. So, there's an open question, which is how should we go about evaluating these systems, right? I have a scene flow method. I claim it's good. What does good look like, right? Naively, you can say, okay, we'll just say on a per point basis, we'll compute endpoint error between the ground truth flow vector and what your method spat out. The problem is that's going to get dominated by describing the background well, right? 85% of the points are from the background in these real scenes. So last year when we ran this competition, Nate cooked up it's called 3-way EP, and you split the world into 3 distinct sets, right? Background, foreground static, foreground dynamic. And the idea here is that you have these very different sized buckets, but in principle, you now have some measure of, the movers that we care about. The problem that we ended up discovering is that this is still dominated by large objects. So we're talking about cars, trucks, that sort of thing, because there's a lot of cars and a lot of trucks in AV, and also there's many points per object. And so you find that there's more than 10 times fewer points on things like pedestrians, bicyclists, VRU as a vulnerable road user. And these are actually objects that are very important and we care about. And we want to be measuring them appropriately. Now, importantly, this isn't just an academic concern. So I'm the author of the Zero Flow method. I evaluated my thing on 3-way EPE. We got state of the art. The numbers were really low. I'm like, oh, cool. Is scene flow solved? I went to go make teaser figures for the paper. And I was like, is my method broken? Because it just simply did not know what pedestrians were. And I thought, okay, well, maybe the other methods work and mine is just uniquely bad. No, none of them do. So you can see on here, this is a pedestrian. This is an unusual scenario in that they're particularly close to the AV. So you have many, many points. Despite this, none of the state-of-the-art methods at the time were able to pick out any sort of motion. And so both methods needed to get better and our metrics needed to reveal that this was actually a problem. So motivated by this, we came up with a new evaluation protocol called bucket normalized EPE. So broad strokes, you probably recognize the class-based breakdown that you see from like MAP evaluations and that sort of thing. But one of the key things that we do is we also segment speeds in this like 2-dimensional matrix, right? So you can see speed columns here, and you essentially evaluate EPE for each one of these buckets, and we normalize the bucket by the speed, right? So if you have a car moving at 30 meters per second, and you have 0.7 meters per second of EPE, that is a smaller percentage of missed description than a pedestrian walking 0.5 meters per second with 0.5 meters per second of error, i.e. you didn't describe its motion at all. So this normalization is very important to getting good descriptions of motion, right? You want to know what percentage of the motion was described well, and you're willing to be more forgiving as a percentage of total motion on objects that are moving fast. So we're able to put together essentially a dynamic normalized EPE score that's, hopefully 0 to 1. If you have more than 1, your error is like really bad. And then we have static EPE, which is just like, how do you perform in the background? If you average over all of these classes, you're able to get a mean static and a mean dynamic error. And so for the purpose of our challenge, we rank every method by mean dynamic score. And so that's what we're really looking for this challenge is, can you actually move the needle on this number, which in aggregate is some statement about like what percentage of motion do you care about over the classes that we are using to break down the taxonomy. With this new evaluation, we also propose a dead simple baseline track flow. But what we do is we take an off-the-shelf detector, right? The detection people have known for a long time that class imbalances are real and matter. and they do a lot of copy paste augmentation, that sort of thing. So we just run a detector on each frame individually, and then we run a Kalman filter. Dead simple, the dumbest thing you can think of to knit these things together. And this we found was like a new state-of-the-art baseline, actually both on three-way EPE and on our metric, where it was significantly better. And so that was the baseline that we put up for the challenge, basically as a point of reference, and asked people, all right, what can we do to beat this? So we ran two tracks. We ran a supervised and an unsupervised track, right? One of the things that James mentioned is this is a very heavily annotated data set. The public number is somewhere in the order of $750,000 to label the train split on this. It would be nice if we could take this and scale to the LiDAR data set, build priors, and we'll see some methods that do that today that don't require this enormous amount of labeling. So these are roughly the results. Our supervised method track flow was beaten by flow 4D, which we'll talk about next, and as well as two very strong unsupervised methods that are quite good. So one of the big things that you can see is that pedestrian and wheeled VRU are where these methods are shining, right? Cars, you're not really getting much additional performance, but it's really these other vehicle category, it's a bit better. And then wheeled VRU and pedestrians, we go from, less than half of the motion being described properly to almost 80% of pedestrian motion being described well. So this is like a pretty significant improvement over what we had even a year ago. So with that, I want to talk about flow 4D. This is a very interesting method because when we put out this challenge, what we expected for people to do is build more intricate loss functions, right? One of the things that people do when they want to do class rebalancing in the detection literature is they do all kinds of copy paste augmentation. They do all kinds of, upweighting for the rare classes. That's what we expected. Turns out that there's actually a tremendous amount of juice left to squeeze in the architectures themselves. So the key takeaway, I think, from this architecture is fuse early and fuse temporally the points. And by that, I mean, if you look at prior literature, what they tend to do is they ran a point pillars backbone on each point cloud individually, fused them after this feature preprocessing, and then computed flow. And it turns out if you fuse them much earlier, so rather than computing features independently and then fusing them together, if you compute features very early on and then do these 4D voxel convolutions, you don't need to change the loss at all. You just get significantly more juice, basically for free. So this is a more detailed diagram from the authors. Basically, they encode all of these points with a time as well as position information, and they're sticking them in these voxel features very early on. And then they have this 4D voxel network. One of the contributions they had is that they were able to do this as a 3+1 deconvolution as opposed to a full 4D. 4D is very expensive. And so they're able to get like the same performance with significant computational savings. So this method is yet to be published. They will release more details when they do. One of the things that I thought was very interesting is they provided an ablation. So they have a 2-frame and a 5-frame version of their method. The 2-frame method is unsurprisingly a little bit worse, but not much, which tells you that really most of the juice that they're squeezing out here is just better architecture design. So I think that one of the big takeaways from this for the community is this architecture is a step function improvement over prior methods. Like, don't use other architectures, build off of this, and maybe take a lot of the key insights that the authors have found and use that to build the next generation of stuff. So I was really excited to see this because they didn't do any loss function tuning at all. They had a standard loss function and got really good results. With that, that was the supervised winner. I'm now talking about the unsupervised track. So Yang Kong is sitting right there. And he is presenting this paper at CVPR. So please go talk to him afterwards and figure out when his presentation is. And with that, I want to tell you about what it does. So I would say that the key insight here is that you can get a lot of juice just by clustering plus doing ICP intelligently on these clusters. One of the big things is we have amodal bounding box annotations. They are rigid motion. Use that information to your advantage. So step 1 is do ego compensation. HD maps allow for ground removal. And what you get are these floating clusters of various objects, be it pedestrians on the sidewalk or cars driving down the road. You can do standard clustering to get these clusters. You then match them. And then really the magic sauce of this method is finding good initialization for ICP. So they do all points pairwise matching. They get a histogram. And then they use that as an initialization to figure out what the transform for ICP should be. Once you have this good init, you have, roughly, hopefully convex optimization service, and you're able to then lock in and get really good flow. And they use ICP for refinement. And so this is like a non-trivial improvement over prior methods. So like fast NSF and NSFP, these are like previous state-of-the-art methods. The jump here is on par with the jump from NSFP to fast NSF. So this is like meaningfully moving the needle. And this is an entirely unsupervised method, right? Zero flow labels. So this is an optimization-based approach. I want to talk about the honorable mention, SE flow, which takes a different look at things. So they were, instead of doing, test time optimization, they want to distill into a student network, and then you have a feed forward network to actually do training and inference with. So the key takeaway from their thing is that, again, there's a foreground, background imbalance. You should actually be able to estimate jointly with your training whether these points are from the foreground or from the background. And this information is useful for class rebalancing purposes. So yeah, like I just said. And importantly, nearest neighbor alone is like kind of a bad prior. So this is taken from the zero flow paper. We looked at what is the error between the ground truth and nearest neighbor as a prior look like. This should be a dot. It's not. It's like, all over the place, right? Something like neural scene flow prior, which we used as a teacher in zero flow to train a student, has a more collapsed error distribution, but it's still pretty significant. So instead of just using raw nearest neighbors, they use nearest neighbors as a noisy estimator to then do nearest neighbors only on motion clusters, and then use that refined two-step process to then train this feed forward student. And what they found is this is much cheaper than running neural scene flow prior, which is a quite expensive test time optimization method. And it also provides better quality flow. James mentioned the LiDAR dataset. This has been, I think, criminally underutilized. But one of the things that they do is, like with zero flow, they're actually able to take their method and scale beyond just the point clouds in the sensor data set. So they show not only do you get good results, as you scale up, you're able to go to 200 or more % of your training data set, and your scaling laws just continue. They only trained to 200% because they were compute limited, not because that's where it bent. So this is like a very exciting path forward as well. So, I want to close by saying the AV2 scene flow challenge remains open. We've had a lot of progress over the last year. I think that this metric really makes clear what is it that we actually care about. And we went from methods that qualitatively kind of didn't work. I mean, I was the author of one of them, so I don't feel bad saying that. To, honestly, these things work pretty well. There's still a lot of juice left to squeeze, and you should stay tuned because I know for a fact that we can do better. But I'm very excited for where the community is heading. I think we've had a lot of breakthroughs recently, and this is like a very fertile ground for more juice left to squeeze. So with that, I want to hand it over to Nihar for end-to-end forecasting.
All right. Thank you, Kyle. So today I'll be talking about the end-to-end forecasting challenge, and I want to start with an observation about the state of AV perception research. And it seems like there are almost two sub-communities within AV perception. And there are folks that work on detection and tracking, and here we're pretty used to working with noisy sensor inputs and intermediate representations. And then we have folks that work on motion forecasting, and different from detection and tracking, the motion forecasting setup assumes ground truth tracks as input. And in recent years, and in large part due to Uni-AD, which was the CVPR'23 best paper, there is significant renewed interest in end-to-end perception. So this is starting from raw sensor data and predicting all the way to forecasts. And in this spirit, we've been hosting the end-to-end forecasting challenge for the last 2 years to facilitate research on this problem using the AV2 sensor data set. So this year, we had 12 teams that participated with over 250 leaderboard submissions. And in this talk, I'll sort of briefly describe some of the progress we've made on these 3 different sub-challenges. So first, I'll start with object detection. So the problem set up here is that methods are required to predict outputs for a 150 meter by 150 meter range over 26 object categories. So notably, this is much larger than comparable data sets. And methods have access to LiDAR and RGB point clouds. So first, before we dive into the methods, let's understand how they're scored. And the primary metric which we score methods on is composite detection score, or CDS. And I'll explain this metric with a small example. So let's go through the example of evaluating car CDS. So here in green, we have ground truth boxes, and in blue, we have predictions. Each prediction has a confidence score. We define predictions that have an overlap with the ground truth using center distance. We call these true positives. We can compute for these true positives, average translation scale and orientation error. And predictions that don't overlap with the ground truth are false positives, and ground truth with no matched predictions are false negatives. So now that we've sort of split up the distribution here, now we can go and compute MAP, and we can compute the other submetrics of the CDS score. So CDS, which is largely inspired by Nucines, is simply a product of MAP and a sum of these normalized true positive scores. Okay, so now that we know how to evaluate these metrics, let's talk about the challenge winner. And this year's challenge winner is a returning competitor from team LE3D E2E. And the key insight from their method is that there's still room to explore new architectures, new and better architectures. And in practice, this team uses Focal Former 3D, which mines hard instances through a multi-stage heat map encoder. And what this means is, in the first stage, they run their standard object detector to find the easy examples, and then they ignore these easy examples and run their detector again to try and find the remaining hard examples. And this better architecture pays tremendous dividends, as we'll see in the metrics. So their method here is an ensemble of ensembles. So they combine the output of their method from last year, which is the LE3D E2E detector, which we'll talk about next, in conjunction with Focal Former 3D. And importantly, Focal Former 3D is a LiDAR-only detector, whereas last year's submission was a multimodal detector. They combine these outputs through late fusion using weighted box fusion. And last year's architecture is a pretty straightforward multimodal fusion approach, where we can represent both RGB and LiDAR data through bird's eye view features, and we can combine these spatially and temporally before detecting things with a deformable deader head. So importantly, this method ensembles 8 different models with respect to different voxel sizes, different resampling strategies. They train some models that are LiDAR only, some models that are multimodal, and they combine all of these post hoc with late fusion or weighted box fusion. So importantly, although, as we'll talk about, this method performs incredibly well, this is far too slow to run on vehicle. But I still think this is interesting for off-board perception purposes. So if we have a large set of unlabeled data, like the Argoverse LiDAR dataset, you can run this to generate some sort of pseudo labels, which can be useful for downstream perception. Okay, so comparing to last year's winner, so LE3D E2E won the competition both this year and last year, we can see they improve on CDS and MAP by 4% each, and they sort of beat all the other true positive metrics. And as I mentioned, the performance is largely due to this better architecture. So Focal Former 3D is really what's allowing this performance improvements. And if we actually break down this performance by range, we'll see that there's a modest improvement in the near field detection of 2%, but we see much more significant improvements from 50 to 100 meters, improving by almost 6%, and then from 100 to 150 meters, improving by almost 7%. So this is incredibly notable because in previous iterations of this competition, we've seen most competitors focus on near range detection. So it's interesting to see that just by adding this new LiDAR-only detector, we're able to do significantly better at long range. Okay, and finally, this method shows better performance across rare categories as well. So as I mentioned, Argoverse 2 evaluates over 26 categories, many of them underrepresented, like strollers and wheelchairs. And we see that we're able to see considerable performance improvements across many of these rare categories as well. Okay, so that sort of summarizes the state of the detection challenge. Moving on to multi-object tracking. The problem setup is very similar to detection, but now we only look at a 50 by 50 meter grid. We still evaluate on the same 26 object categories, and the inputs are the same. This challenge is evaluated using a higher order tracking accuracy, which decomposes tracking into detection scores, association scores, and localization scores. So this is a very standard metric used in 2D tracking, and we simply repurpose this for 3D. And the challenge winner for this track is also team LE3D-E2E. And this is really not surprising considering that they use a training-free tracker, specifically AB3D-MOT. And for those of you familiar with the tracking by detection pipeline, given really strong detections, it's quite straightforward to sort of build a really strong tracker as well. So the top two teams used AB3D-MOT, and this is in stark contrast to last year's method from the same team, which used a learning-based tracker. So importantly, they use Motor, which is sort of an end-to-end learnable framework, which uses object queries from the object detector and sort of learns to associate objects over time. So simple trackers still seem to work incredibly well given strong detectors. And we can see this sort of play out in the metrics as well. So this year's winning team improves HOTA by 8%, AMOTA by 7%, MOTA by more than 10%. So all of this is really just because they spent a lot of time and effort tuning up their detector. So it still seems like, you know, if you have a really strong detector, tracking sort of becomes a much more simpler problem. Okay. We can compare the performance between the first place team, which is LE3D-E2E, and the second place team, Vallejo Forecast. And importantly, both methods here use the same exact tracker. So the performance delta between these two methods is strictly due to differences in detection quality. So I think that's interesting to note here. And that sort of wraps up the tracking side of things. And I think the most interesting part is end-to-end forecasting. So this end-to-end forecasting challenge also looks at a range of 50 by 50 meter grid. And different from most traditional forecasting datasets, we want to evaluate forecasting for 26 object categories. And the inputs remain the same as all the other sub-challenges. Importantly, methods are allowed to look at an unbounded history and are asked to predict the motion of all agents for the next 3 seconds. And we can reuse the sensor dataset, although this dataset wasn't meant for the task of motion forecasting. We can turn the track level annotations into forecasting annotations by sequestering parts of the track. And for this, we propose a new metric called forecasting MAP. And this metric is heavily inspired by MAP. And the only difference here is we tweak the definition of what it means to be a true positive. So in this forecasting MAP metric, we define a true positive to be one where the prediction and ground truth overlap at both the current time step and the final time step. And once we sort of modify the definition of true positive, we can simply compute MAP as normal. And importantly, the sensor data set, as I mentioned, is not really meant for motion forecasting. So what we find is most of the objects in the scene are static. So 71.2% of all actors in the scene are static. And we see about 28% of actors having some sort of dynamic motion. And this has notable impacts on algorithm design. So if we naively evaluated forecasting accuracy on the entire subset, which is dominated by static actors, we'll find that you can do really well by predicting that everything moves with constant velocity or doesn't move at all. So to solve this problem, we can break down evaluation by different motion subcategories, and we define 3. So static subcategory, the static bucket is defined by detections or trajectories where the final position is approximated by no motion. The linear bucket is where the trajectories or the final position is well approximated by constant velocity, and we bucket everything else into nonlinear trajectories. And we can compute a final MAP or forecasting MAP score by simply averaging performance across these 3 buckets. And the winner of this sub-challenge is the team Vallejo Forecast. And interestingly, they repurpose leading motion forecasting methods, such as MTR. And it's interesting to note that this method in particular won the Waymo motion forecasting challenge in 2022. So this method jointly predicts global agent intentions and local trajectory refinements. But I think the most important thing about this approach is not their method, it's not their architecture, but rather the way in which they train their method. So first, they pre-train MTR on 1,300 hours of motion forecasting dataset. So using a framework called Unitraj, they combine the new scenes dataset, AV2 motion forecasting dataset, and the Waymo motion forecasting dataset, and they use this to pre-train MTR. And they train the model on the roughly 30% of dynamic movers within the AV2 sensor dataset. Next, they fine-tune their model with perception augmented trajectories. And what this means is that they replace ground truth trajectory history with projected tracks. So this is meant to reduce the distribution gap between your perception outputs and your ground truth trajectory forecasting datasets. And they keep the ground truth forecasting targets. And then lastly, they apply a post-processing step. So as I mentioned, they only train on the dynamic movers. So this biases their method to predict that everything will be moving. But as we saw in the distribution of movers, most things in the data set are not moving. So they simply replace the lowest confidence prediction within their top K set of predictions with a static forecast. And interestingly, this is very similar to last year's top performer, which uses data augmentation to also reduce distribution shift. But different from this year's method, they jitter trajectories with Gaussian noise, and they drop detections and interpolate trajectory history to increase the size of the data sets. Okay, so we can compare the performance between Vallejo Forecast and LE3D E2E, and we see a substantial improvement in performance. So despite Vallejo Forecast having lower quality detection and track predictions, they're able to get 13% higher MAPF compared to the second place team. And the performance really translates to nonlinear movers, where they're able to get more than 38% improvement. And this improvement is really due to their data augmentation and fine-tuning of perception outputs and post-processing steps here. So with that, that will conclude the end-to-end forecasting challenge. But we still have another forecasting challenge, which I want to talk about, which is the multi-agent forecasting challenge. And this is sort of the longest running of the Argoverse challenges. And we've run this challenge for 6 years, for the last 6 years, starting all the way back in NeurIPS 2019. And every year, we've sort of spent a lot of time and effort to improve the evaluation setup, introduce new ranking metrics. And year over year, the community has continued to impress us by improving motion forecasting performance across all of our different tasks. So a little bit of history here. The Argoverse 2 motion forecasting dataset was first introduced in 2022 and contains 250 scenarios across 6 different cities. And at the time of publication, this dataset was among the largest and most geographically diverse datasets publicly released to the community. And importantly, the AV2 motion forecasting dataset, unlike the sensor dataset, is highly curated to have challenging motion forecasting scenarios. So this dataset is chock full of AV-relevant interactions with socially complex environments. And we also look at interactions between the ego vehicle and non-vehicle actors. So the first iteration of the AV2 motion forecasting challenge, which we ran in 2022, only focused on the task of single agent forecasting, where we wanted to forecast the motion of a single focal agent. So this is an agent which we deem to be interesting and important within the scene. But importantly, this is sort of a limited subset of what we should really look at if we want to build safe autonomous vehicles. And safe planning, importantly, requires that we forecast the joint probability of all agents in the scene. So this sort of motivated the shift from single agent forecasting to multi-agent forecasting. And we instantiated this multi-agent forecasting through this concept of multiple worlds. So within each of these worlds, we want to predict the joint future states for all actors. So here is an example of world 1, and each world is assigned a different likelihood. Each of these likelihoods is normalized such that we can sum up the probabilities to equal 1. And this problem setup is very similar to motion forecasting challenges in previous years, where we assume 5 seconds of history. We know exactly the inferred actor types, and we have access to a local static map. And methods are required to output normalized probabilities for 6 predicted future worlds. And within each of these future worlds, all scored actors will need to predict a different trajectory. We'll need to predict trajectories for 6 seconds. And importantly, we only evaluate scored actors, which we deem important for planning. So before we can talk about how to evaluate this multi-world, multi-agent forecasting problem, let's quickly refresh ourselves on single-agent forecasting metrics. So importantly, there are 3 metrics here. First is min FDE, which measures the distance between the best prediction and the ground truth at the final time step. Next, we have miss rate, which is the proportion of actors with a min FDE greater than 2 meters. And we have a Breyer min FDE, which is simply just min FDE with an added penalty for low confidence predictions. And we can take each of these single agent forecasting metrics and turn them into multi-world forecasting metrics. So min FDE turns into min world FDE, which is simply computing the lowest min FDE out of all predicted worlds. Miss rate turns into actor miss rate, which is the proportion of scored actors with min FDE greater than 2 meters in your best world. And lastly, we have Breyer min FDE, which naturally follows from Breyer FDE. Okay, so we've had a great number of submissions to this challenge this year. So we've had 300 submissions across 16 teams. Many of these teams submitted across leaderboards, including the Argoverse 1 motion forecasting challenge. And we had many entries from top teams of previous Argoverse forecasting competitions. And this year's winner is Light QCNet, lightweight query-centric trajectory prediction. And interestingly, there was a lot of tight competition towards the end. So Light QCNet beat out the second place method, LOF, by just 1%. So there was a lot of healthy competition going on in this challenge. So to briefly talk about Light QCNet, we first need to refresh ourselves with QCNet, which was the winner of last year's challenge. And Light QCNet simply modifies QCNet using patch-based attention modules, which are inspired by Behavior GPT. And if I'm not mistaken, Behavior GPT is one of the top competitors on the Waymo Sim Agents challenge. So by simply swapping out this patch-based attention, this method was able to show improved training speeds and reduced memory consumptions by 45%. And they're able to do all of this without having to sacrifice any accuracy or performance. Now, moving on to the single agent challenge results, we've had 300 submissions across 40 teams in this similarly tight time span. And interestingly, people were able to improve by 11% year over year in min FDE. So the best method here from 2024 is FutureNet LOF, joint trajectory prediction, and lane occupancy field prediction with future context encoding. And again, we had a very tight competition here between the first and second place winners. So I just want to highlight Sept++ was trailing just by 1%. So this was a really tight race towards the end. Okay, so FutureNet LOF incorporates recurrent context from predictions across all actors and predicts lane occupancy fields to jointly reason about goals and behaviors of all actors within a local spatial region. So interestingly, although this is a single agent forecasting method that achieves the top performance on the AV1 and AV2 single agent forecasting leaderboards, it also shows incredibly strong performance on the AV2 multi-world forecasting challenge without ever explicitly being defined or designed for this task. So to conclude, I think there's a significant amount of interest in end-to-end forecasting and these challenges as a whole, but there remain a number of open questions. So first, we have this distinction between end-to-end versus stage-wise methods. So the top performer last year used an end-to-end method, whereas this year we're seeing the top performing teams using stage-wise methods. And although there are benefits to each, I think it still remains to be seen which one wins out on top. We also see that there is a lot of scope for leveraging trajectory level motion forecasting data within the end-to-end forecasting challenge. So the winner of this year's forecasting task, Vallejo Forecast, demonstrated that you can pre-train on 1,300 hours of motion forecasting data. And they're only able to do this because they're a stage-wise approach. Lastly, we see that data augmentation remains an incredibly important component when we try to bridge the end-to-end and standard motion forecasting tasks. So although the winner of the motion forecasting task, Vallejo Forecast, used one of the previous winners of the standard forecasting task, they had to spend considerable effort to bridge the gap and perform some sort of data augmentation to make it easier to work with predicted outputs or predicted perception outputs. And lastly, the key challenge that still remains is improving runtime for on-car deployment. So the winning detection method, which we highlighted, is an ensemble of ensembles with maybe 15 models under the hood. So I think it would never be feasible to try and run this in practice. So I think if we want to try and distill some of the learnings from this challenge into real on-car products, I think there still remains to be a lot of progress that needs to be made in this direction. So with that, I'll hand it off to Tarasha to talk about 4D occupancy forecasting.
Cool, thanks, Nehar. This is the last forecasting challenge for you all, hopefully. So I'm Tarasha, and I'm a PhD student at Carnegie Mellon University. Can you hear me now? Okay. I'm a PhD student at Carnegie Mellon University. I'm Tarasha, and I hosted the 4D Occupancy Forecasting Challenge this year, which I'm presenting today. Let me start by talking about the task of 4D occupancy forecasting and why it holds relevance in the autonomous navigation stack. So recall that for perception and prediction tasks that we talked about till now, lots of costly human annotation is needed in the form of object tracks, labels, and HD maps of cities. But this annotation process is not really scalable. So we want to encourage tasks and methods that do not rely on these annotations and are rather self-supervised, so that they can take advantage of the ginormous amount of data that is being collected by autonomous fleets every day. So one such task in the autonomous driving world is called point cloud forecasting. Given a set of past LiDAR sweeps, it aims at predicting the future LiDAR sweeps. And no annotations are needed for this task because the ground truth is already available in the archival logs. Now, while this seems straightforward, understanding where every point in the point cloud is going to lie in the future is non-trivial. And that is because points depend on the intersection of rays from the LiDAR sensor and the environment. And these rays change with the change in the motion of the autonomous vehicle and the ray sampling pattern of the LiDAR sensor. So then accurately forecasting points requires accurately forecasting extrinsics and the sensor intrinsics and the motion of the environment. So we argue that from an autonomy standpoint, it only makes sense for the autonomous systems to make predictions about the environment that they are in and not the calibrated LiDAR sensor that they are equipped with. And to this end, instead of directly learning to forecast points, we propose that methods instead learn and forecast the underlying occupancy of the world. And once we have this occupancy, we can easily render it into future point clouds. So this brings us to a problem setup where we learn a more useful and generic quantity from exactly the same training data as point cloud forecasting, but without any annotations. And we call this task 4D occupancy forecasting. All right, but then how does one even evaluate occupancy? because of course we don't have access to the ground truth occupancy, which would have been the gold standard, but we do have point clouds that can be rendered from this occupancy. So for evaluation, we give methods query rays, along which they have to predict the distance that this ray travels before hitting a surface. And based on this distance, we calculate the L1 error and the absolute relative errors as our primary evaluation metrics. So for the second iteration of this challenge, similar to last year, we allowed methods to look at the past 3 seconds of data and ask them to forecast the next 3 seconds. And we defined a bounded volume called the near field volume within which all the metrics were computed. Traditionally, chamfer distance is also used for evaluating point cloud forecasting. So we compute that inside the near field volume and then also on the unbounded point cloud. And finally, this challenge was relatively popular this year, and we got a total of 42 submissions as compared to last year. And we had started the challenge last year with 2 baselines. The first one was a simple ray tracing baseline, which was based on an aggregation of past point clouds. And then the second baseline was a self-supervised method, which predicts 3D occupancy grid for every future time step. And then self-supervises using the ground truth point clouds after differentiable rendering. So the winner for the challenge last year relatively improved our ranking metric, which is the L1 error, by 8%. And this year, we had methods pushing the state of the art even further, relatively improving the L1 error by 24%. And I'm happy to announce that this year's challenge winner was Team Uno from WABI and University of Toronto. And so they requested to present their method, and I invite them, specifically the authors Ben and Quinton, to take it away from here.
All right. Hello, everyone. My name is Quinn. This is Ben, and we're going to be presenting our submission to the Argoverse Occupancy Challenge Uno, a 4D occupancy foundation model. So Uno is a foundation model that is designed for the physical world. The way it actually operates is you give it a continuous point in space and future time, and it'll tell you if this point is going to be occupied. We also showed that it can be transferred to a variety of different downstream tasks, such as that of LiDAR forecasting, and also the task of bird's eye view semantic occupancy forecasting. So how do you actually go from unsupervised LiDAR information to occupancy labels? Well, the way you do this is by taking a closer look at the information you get at each individual LiDAR array. So if you trace the position of the LiDAR to every single point in the scene, you get some kind of information about which regions of the scene are unoccupied, since otherwise LiDAR would have stopped earlier. It also tells you that there must be a small region of occupied space behind every single LiDAR array, since this needs to exist to reflect the actual LiDAR itself. Now, this is pretty sparse supervision, but if we rely on the fact that neural networks are generally pretty good at generalizing and filling in the gaps, this actually allows you to get a pretty good supervision for all the occupancy in the scene, especially if you can balance the total number of sampled unoccupied and occupied points that you use during training. So more specifically, this is kind of how our architecture works to do all of this in a continuous manner. You take the past LiDAR sweeps, you put it into a voxelizer with the timing and intensity information, you put it into a LiDAR encoder, which produces you a bird's eye view feature map. And now let's take a single look at a single quarry point. So what you do is you take the bird's eye view feature map you got from the LiDAR and you interpolate it at the XY location of the quarry point you're looking at. This can be used to give you an attention offset, essentially telling you where else in the scene to look for other information. And this can be used to, again, interpolate a secondary feature vector. Taking it all together, you can use this information to produce your future occupancy predictions. So this is really nice because, one, it can run in real time in a large number of different query points, allowing you to actually, again, render larger scenes. Two, it has a larger receptive field because of the deformable attention, so that allows you to basically track fast-moving vehicles that maybe exist in the scene. And finally, most foreground motion that you care about in self-driving scenes happen in the bird's eye view plane. So this kind of summarizes this and distills the information into the regions in the actual format that you care about.
Yeah, so as Quinn said earlier, to perform LiDAR forecasting, we want to leverage UNO's understanding of the geometry and dynamics that it has in its occupancy. And to do so, we attach a small learned renderer, which transforms UNO's 40 occupancy fields into LiDAR point clouds. The learned renderer takes a query array as input, and in turn queries UNO for occupancy values at regular intervals along that array. These occupancy values, along with their positional encodings, are fed into a small MLP, which predicts the LiDAR point depth and is trained with an L1 loss against the true LiDAR point depth. So we have a qualitative example here, where on the left we have UNO's, let me put this in loop, UNO's point cloud forecast, and then the ground truth future point cloud. And we can see that UNO is pretty good at capturing moving vehicles, which we found that previous methods weren't so good at, such as this turning actor here. And this here is actually a small cyclist. And we get, as discussed earlier, large relative improvement from previous methods across all the metrics. So here we can look at the 40 occupancy forecasts underlying these point cloud predictions of both UNO and the previous year's method 40 OC. So let me just loop this. So here you can see that 40 OC struggles to generalize beyond the point cloud input and predicts all actors to be static, whereas UNO has a good understanding of the dynamic actors. And again, you see this turning vehicle here represented well in the occupancy and the cyclist here. Thank you for listening. And if you have any questions, we have a poster session later this week, so come to that.
Cool, thanks guys. Up next. Okay, I want to announce the runner-up of the 40 occupancy forecasting challenge, which was Team NLK from DGIST and Naver Labs. The method that they developed is largely based off of the self-supervised pipeline that we saw before, except that the 4D encoder decoder, or specifically the unit, is slightly different. Specifically, the input LiDAR sweeps are used to construct a single 3D voxel volume, which is then passed through a feature extractor and an encoder, once again to predict a single bird's eye view feature map. And then this feature map is passed through a temporal decoder, which predicts occupancy features for each future time step with information from the previous time step. And then finally, there's a occupancy classification layer, which classifies each voxel of the future occupancy grids into whether the voxel is occupied or not. And this is surprisingly effective in capturing dense information about the occupancy of the world as compared to the last year's baseline, which was 40 OC, as you can see here. And for both the winning methods, I am showing a high-level overview of their pipelines. And the one thing which is evident is that both methods use an intermediate bird's eye view feature map to bottleneck their pipelines. So even though the input and the output are in 4D, which is in 3D space and time, the right intermediate representation seems to be the bird's eye view feature maps, likely because they can capture any dominant and relevant motion in the scene for driving. Finally, in general, for occupancy forecasting, I think we still need to think about how to forecast multimodal futures while learning the driving dynamics, and then also tying in quantities like scene flow, which can be used to represent physical constraints like conservation laws for occupancy. And with that, we come to the end of this year's Argoverse challenges, and all the challenges are going to remain open even after CVPR, and we'd like to encourage you to submit to them, and we can take any questions you would have now.